Okay, recording has started. All right, so good morning, everybody. Welcome back to Math 115. So a couple of announcements before we start class today. The first of which is our first exam is going to be on February 4th. That is 1 week from today. Okay, so that'll be 1 week from today. So next week, here's what we're gonna do. Today, we are going to cover section 1.4. I'm going to try to get through all of it. Next week, I'm going to try to do, let's see, this will be 1.5 will be on Monday. 1.6 and 1.7 will be on Tuesday. Review will be on Wednesday. And then our exam will be on Thursday. Okay, so that's the plan. I've written a practice exam for you all, okay, which I'm going to post to the Blackboard page today. I just have to look through it one more time and make sure there's no typos anywhere on it. So the practice exam is really just designed to give you an idea of how I ask questions on exams, because it can be a little bit different than what you might be used to with your typical math exam when you're in person. Okay, so for an in-person math exam, it makes sense to ask questions like, okay, why wouldn't I ask that question for you guys? I'd ask, I don't know, factor this polynomial or something like that. But, you know, any person who wants to be academically dishonest at home can just go ahead and go online and search, you know, factor this polynomial, and up will pop the answer, and they can just get full points for that. So to sort of like mitigate that issue, I ask a lot of conceptual questions on my exams when I'm teaching online, and that's to kind of test whether you have an idea of what's going on. So I might not ask you to use the quadratic formula to solve for the roots of this equation. I might ask you, what is the purpose of the quadratic formula and what would you use it for? And something like that. Okay, and that's a little bit more involved. So the practice exam should show you the types of questions that I'm going to ask, but it's really not designed to be the only way that you study for the exam. It's designed to help you and give you a flavor of what the exam will be like, but the actual content of a 5 to 7 question exam can't really cover everything that we've done so far. So there's going to be some gaps in the practice exam, and there will be some gaps in the exam, and there will probably be some overlap, but it certainly won't cover everything that's on the exam. If you want to do that, you need to do the homeworks. You need to look at the notes. You need to look at the book, check the practice problems in the back of the book, and all that sort of stuff. So if you need help studying, let me know and I can help give you some tips. But by far and away, best way for you guys to study for this exam on next Thursday is going to be to come to office hours on this coming Monday and next Wednesday. Those are going to be the best sort of bang for your buck in terms of time spent studying. You can learn the most when you're working with me, probably. Well, and that's not me claiming that I'm so great or something, but that's just saying most students learn better with an instructor. So if you want to spend as little time possible studying, those would be the times that I would block off. Also the SI sessions. Okay, so are there any questions from anybody about the exam or how that's going to work? How many questions would it typically be? I usually do like 5 to 7 questions, but most of them will be like, you'll have like 1 through 5, but each question will have like A, B, or maybe A, B, and C and D sometimes, but it's designed to take students like an hour or maybe an hour and a half. So it'll be taken remotely. So what I will do is, so the question coming in is, will it be on Blackboard or MATLAB? Kind of neither. It's not going to be it's not going to be like a multiple choice type of thing. It's going to be a free response. So I'll post the exam to Blackboard. You can download it as a PDF. If you want to, you can print it out and fill it out on the paper, or you can just fill out your answers on a blank sheet of paper, and then you'll have to scan it as a PDF. Okay, you can use your phone, or if you don't have a phone or a scanner, let me know. But you can use your phone, you use a scanning app or whatever, and you'll scan it as a PDF, and then you'll submit it to Blackboard by 9 p.m. So you'll have like a 12-hour window to do an exam, which should take you certainly no more than 2 hours to complete. Okay, so how many questions would it typically be? I answered that one. In which platform? I answered that. If we do the practice exam, could we send you our answers for you to look over and tell us what we did wrong? Yes, you could. I'm also going to post a solution guide to the practice exam. Okay, one sec, Savannah. Let me finish answering Morgan's question. So if we do the practice exam, could we send you our answers for me to look over? Yeah, you could, and I'll look over them. The best way to do that would be to schedule an appointment with me where I can talk it over with you directly. But I am going to post a solution guide to the practice exam. Typically, I give students a few days to try it, and then I post onto my YouTube channel a video of me solving the practice exam and explaining everything about how I'm solving it, why I'm solving it, the methods that I'm choosing, and I go kind of into detail on all of the questions. And I reference where this is coming from in the material and that sort of thing. So it's usually a pretty comprehensive guide. Most students just find that to be sufficient, but I definitely do recommend that you try the practice exam before you look at the solution, because you want to have a good idea of how well you understand the material before you look at how well I can present it. Okay, so Savannah asked, I'm a little confused. Do we need to print off the exam, or is it digitally downloaded and done online? You don't need to print off the exam. I will post a PDF of the exam to Blackboard, okay? And it will become available at 9 a.m. on Thursday. So at 9 a.m. on Thursday, you'll go to Blackboard, you'll click on assignments, and you'll see exam 1. You'll click on that, and up will pop a file on your screen, which will be all of the questions for the exam. From there, you can do one of 2 things. If you want to, you can print that out, and then you can do the exam on that paper like you would do a usual math exam. If you don't have a printer, or if you don't want to waste paper or whatever, then what you can do is you can keep the questions on your computer screen, and you can fill out your answers to the questions on your notebook. Regardless of which method you choose, once you have all of your written answers on some paper of some kind, you just have to use your phone to digitally scan it and get it collected, all of your pages of work collected into a single PDF document, and then you will upload that to the assignment submission on Blackboard. Does that make sense, Savannah? Okay, cool. All right, if there's any other questions, just let me know. Correct, no class on Thursday. Yeah, so theoretically you could do the exam during our class time. Oh, I guess I'd have to post it at 8:30. Yeah, I guess I'll post it at 8:20 or something like that, so that you could theoretically do it during our class time if you have other commitments every other hour of the day. But yeah, we won't have class that day. Okay, cool. Well then, if there are no other questions, we'll move on and talk about math. So where was I? Okay, so let's briefly recall what we did last time. We talked about domain and range mainly. We talked about how to find the domain of a function when we're just given the function rule and we're not necessarily given like a collection of points where we can find all of the x values of those points, and that would be the domain. We have to take the rule and just assume the domain to be the largest set of real values for which the function has a sensible output. Okay, so we had to avoid things which would be nonsensical, such as dividing by 0 or taking the square root of a negative number or an even-powered root of a negative number. Okay, so we had to make sure that if we have a square root, we need to exclude any x values which would cause whatever's underneath the square root to be negative. And if we have a fraction, we need to exclude any x values which would cause the denominator to become 0. So that was the domain. And then we talked a little bit about range. And to be honest, I'm not thrilled with the presentation of range which I was able to give, because I feel like we need a little bit more material that we're going to learn later on for me to explain that better. So if you don't totally understand range at this time, that's okay. We're going to talk a lot more about it later, and hopefully I can give a better explanation. But the long short of it is basically we just take every single point in our domain, plug it into the function, and find all of the values which are given from it. Okay, so all of the possible values that our function gives when it is applied to a value which is in the domain. Okay, graphically speaking, we had this one where we had the parabola. The domain was just the set of x values, and then the range was the set of y values for which we were able to get that y value by plugging in something in the domain. Okay, so the other way we kind of thought about the range was that the range is the set of possible y values, so things here on our y-axis, such that if we put a point there and we drew a horizontal line, it would intersect our function at some point which is in the domain. Okay, at some point which is in the domain. So that's kind of how that worked. Okay. So then we talked about how to find the domain and range from a graph. We looked at this one here. We just saw, well, if we have a continuous function, which we can draw without picking up our pencil, then the range is just going to be the smallest possible y value all the way up to the largest possible y value. And the domain is going to be the smallest possible x value up to the largest possible x value. Okay. And we do need to be careful if we were to have something like a hole here on our graph where our function isn't defined. we have to make sure that we exclude that point from the domain. Okay, so that's something to be careful about. Okay, then we talked about average rate of change, and we said, well, I said that this is kind of weird that we're talking about this in this chapter, which it is, but I gave you the best description that I can give for average rate of change without really talking about calculus, which was to say it's kind of like the slope of the direct path between 2 points will be the average rate of change of a function. And I guess I can say a little bit more, which is like, if you consider the rate of change of a function at a given point is kind of like if you were riding a roller coaster on this thing. So here's you on a roller coaster, and you considered the direction that you were traveling at a given time. Sometimes you're traveling up, and sometimes you're traveling down. But if you took a snapshot of yourself at every second, actually every nanosecond, even more than that, every infinitesimal unit of measurement of time. What is this? Okay. And you took these arrows and you kind of just averaged up all the directions of all of these arrows into one arrow that summarizes the general direction that you've been going this entire time. It would be this arrow, which I've drawn on our red guy here. It would be that direction. Okay, that's kind of the average direction that we're traveling on our roller coaster from A to B. Okay, so that's really the best way I can describe average rate of change. It's just the slope of the direct path between those 2 points. And we know how to find the slope of the direct path between 2 points. It's just going to be the rise over the run, right? We went up from f of a to f of b, so the rise was f of b minus f of a. And then the run is just going to be b minus a. So that's how we find that slope. Okay, so that's where we left off last time. So now we're going to talk about some new stuff. So we'll talk really quickly about difference quotients. So a difference quotient, I guess we can say a difference quotient of a function, f of x, is a fraction. That's why we use the word quotient. And it's the following fraction. It's the fraction where we plug in f of x plus h, and we divide and we subtract f of x, and then we divide by h. Okay, this is what a difference quotient is. Okay, so h is typically just some number, but we write h because we want to be able to plug in any number that we want. In calculus, we're often interested in plugging in the number 0, for example. Okay. And the difference quotient is kind of like a progenitor of the derivative. Okay, so in calculus, if you're going to take a calculus course, you will probably learn about derivatives, and this is kind of leading into that direction. So this is why we talk about it in this class. So we just define it to be this quotient of these things here. So for example, we could try to find the difference quotient of this function, f of x equals 2x squared minus 3x plus 5, and all we would do is just plug in x plus h. So anywhere I see an x, I'm going to plug in x plus h, with parentheses, of course, and subtract 3 times x plus h, and then I will add 5, and now I'm going to subtract 2x squared minus 3x plus 5, and I'm going to divide all of that by h. Okay, and the process for doing these difference quotient problems is just to write this down by plugging in x plus h and x and dividing by h, and then we have to simplify. And the amazing thing about most of these difference quotients is that we're gonna, at the end, be able to take a GCF of h out of the top, and this h on the bottom is gonna cancel. But let's see if that's true for this case. So if we distribute everything out and we FOIL, we're gonna get 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 5 minus 2x squared plus 3x minus 5. Okay, so that's what we're going to get. And all divided by h. And so now I can do some canceling. In particular, I see this 2x squared can be canceled out with the minus 2x squared later on. Also, the minus 3x can be canceled out with the plus 3x. And the plus 5 can be canceled out with the minus 5. And let's just rewrite what we have so far. We've got 2h squared. Why don't I write it the other way? Oh, right, 4xh plus 2h squared minus 3h all divided by h. And we can see that each term in the top has at least one power of h. So I can cancel on the bottom. This will become a 1. This one will become a 1. This one will become just a h to the power 1. And this one will become a 1. So we will get 4x minus 3 plus 2h. Okay? So this is kind of the amazing thing about difference quotients, is a lot of the time when we plug in this x plus h and then we subtract f of x, we get a bunch of stuff which has h as a factor. So when we divide out this h, we can just cancel everything, and we're going to get something kind of nice and tidy. Okay, so that's what a difference quotient is. We probably won't work that much with difference quotients, but I want everyone to be aware of what they are, so that they're not confused when they come to calculus, because this is how we learn how to do derivatives, is by doing lots and lots of difference quotients and taking limits of difference quotients. Okay. Any questions about difference quotients, or really any of the stuff that we did last time? Anything that's cropped up in your mind since then? Okay. If not, then we'll move on. So this is a new section. This is section 1.4, which has all to do with, well, we learn a couple of function properties, okay, including increasing, decreasing, constant. We learn about maxes and mins. We learn about even and odd functions. We learn about piecewise functions, and then we're going to learn a whole bunch of common functions, which we need to kind of memorize in life in general, I guess. Okay, so let's start at the beginning. So I just want to remind everyone first the form which linear functions take. They'll look like f of x equals ax plus b. And I want to remind everyone that quadratic functions take the form f of x equals ax squared plus bx plus c. And remember here where a and b are numbers. And specifically, a should not be equal to 0. And here we get the same thing. I don't know. We should get again a, b, and c are numbers, and a is not equal to 0. Because if you think for a second, if we had a quadratic function and a was equal to 0, then this term would just go away and we'd be left with bx plus c. And that wouldn't be a quadratic function, would it? It would be a linear function. Okay, so a should not be 0. So you can keep playing this game if you want. You can go ... cubic functions ... and so on and so forth. Yeah. Okay. Whoa, that was not so good. So now let's talk about what it means for something to be an increasing function. Okay, we want to talk about what it means for f of x to be an increasing function. Okay, well, we can think of things that increase. For example, a lot of you might be well aware of what's going on with the stock market right now. So what's happening with the stock market right now is a bunch of Redditors are trying to stick it to the man by like hyper-inflating GameStop stock. And when we say that the stock is increasing, we mean that it's looking like this and then bam, it's going way up, right? That's what it means for GameStop stock to be blowing up. Okay, it's going up as we move to the right. Okay, now in the stock market, we're talking about dollars here per share. And on the x-axis, we're talking about time. Okay. So what we mean is that as we move to the right, the height of our function is going up. Okay, it's getting larger and larger as we move to the right. Okay, that's what it means for something to be an increasing function. Okay, so let's make it formal with some mathematics here. What we say is we take two x values, x1 and x2, and we say that if x1 is less than x2, and x1 and x2 are both in our interval, then we should have that the height of the point on the left should be less than the height of the point on the right. Okay? So in particular for us, we could take a look at our GME stock, and we could take a look at a section here. Here's A, and here's B. So if we take any x1 and x2, which are between those two, with x1 being to the left of x2, so here's x1, and here's x2, the property that should be satisfied should be that the point here, f of x1, should be lower than the point f of x2. Okay? So if x2 is to the right of x1, then f of x2 is above f of x1. That's what it means for a function to be increasing. And we need that to be true for any x1 and x2 that I choose, which are in between a and b. Okay, any x1 and x2 which I choose between a and b, as long as x2 is to the right of x1. Okay, so we have this property here. We have a is less than x1 is less than x2 is less than b, right? What that means is if we read our points from left to right, they should go a, x1, x2, b. Okay, now where x1 and x2 are in this interval shouldn't matter. If it's an increasing function, we could also take these 2 points, right? There and end up here. Or we could take 2 points which are really, really close together. And it should still be true, okay? We should be going up as we move from left to right. Okay. So any questions about what it means for something to be an increasing function? I think this is a fairly intuitive concept. It just means we're going up. Okay. All right, notice also that all of these inequalities in this definition are strict inequalities. Okay, we've got less than and less than and less than and less than. Okay, not less than or equal to. Okay. If we had f of x1 less than or equal to f of x2, we call this non-decreasing, which is not the same as increasing because it could be staying a constant. Okay, a constant function is non-decreasing. Okay, so that's just a little side note. So now let's talk about decreasing. And well, as you might expect, it's going to be basically the opposite. We still choose a less than x1 less than x2 less than b, but now we require that f of x1 should be strictly larger than f of x2. So what does that look like? Well, if we have a graph, and I don't think I have as good of an example for a decreasing function as I do for my increasing function, but we can just take f of x to look like the following. Maybe it looks like this. Got a here, b here, and the point is that if we take any x1 and x2 in this interval, in fact, let me do something clever here for a demonstration. Whoa. Okay, here's my clever thing. Let's copy these. If I take any x1 and x2 anywhere in this interval, okay, as long as we are in between these 2 points here, okay, these 2 endpoints, the property that I should have should be that if I draw a line up to the point above x2, it should be lower than the line which I draw up above x1. Okay, so as we're moving to the right, we should be moving down. Okay, so in particular, it's really a statement about this distance here. We should have f of x2 should be lower than f of x1. Okay, it's an if-then statement. If for any x1, well, if we have this property, basically. Yeah. Okay. Any questions about increasing and decreasing functions? Okay, no questions. Same deal. If we have greater than or equal to, we call that, quote, non-increasing. Okay. So a constant function is kind of what you think. It's if we have some interval a to b, the property that a constant function should have is that it should have the same height everywhere in this interval. Okay, so we choose any x1 and x2 in our interval, with x1 being strictly to the left of x2. The heights of the 2 points which we get should be the same. Okay. Now, one thing that I do want to point out about these properties, okay, is they're what we call local properties. Okay, when I say that something is a local property, what I mean is that f of x is constant function on AB. Okay, so f of x might be a function which looks something really crazy elsewhere. It could look like this. Okay. But we would still say that f of x is a constant function on AB, okay? On AB, what we mean is that locally, if we look at f of x just in between my two goalposts from A to B, it's going to be a constant function. Okay? Now this function, this particular example, we could draw another point over here, C, and we would say f of x is increasing on B comma C. Okay, so when I say that these are local properties, what I mean is that sometimes a function might be constant, and sometimes elsewhere it might be increasing or decreasing, or non-increasing, or non-decreasing. Okay, so these are local properties. What I mean by local is that locally, just here in between A and B, we're a constant, whereas locally, just here between B and C, we're increasing, and so on and so forth. Okay, if I omit this statement about being a constant function or an increasing function like on A comma B, if I just get rid of this part and I just say that f of x is a constant function, then I mean that f of x is a constant function locally for every choice of a local environment. Okay? So if I get rid of that, I really do mean in the traditional sense that it would be constant everywhere. Okay, but we specify these definitions with this a comma b so that we can be a little bit more specific for functions which are maybe sometimes constant, sometimes increasing, sometimes decreasing. Okay, so that's increasing, decreasing, and constant. Okay, so now let's talk about maximums and minimums. Okay, and I think that probably everyone is familiar with the notion of a maximum and a minimum. But what you might not be so familiar with is the modifier relative here. Okay, relative. Okay, and what that means, what relative means is like, I might be, for example, I mean, this isn't true, but I might be like the best at math relative to my graduate classmates or something like that. Okay, that doesn't mean that I'm the best at math ever. It just means that when I compare to a smaller subset of individuals, then I can have that property. Okay, like I said, I don't have that property, but it would be cool if I did. So what that means for the graph of a function is the following. We might have some function which has lots of ups and downs, like this, for example. Okay. When we talk about the maximum of this function, I think pretty much everybody would be able to point up here to this point here, right? It's the tippy top of the mountain, or the roller coaster, if you will, right? But when I talk about a relative maximum, the definition is as follows. We call f of a relative maximum if we can choose, if we can find a subinterval c comma d of the domain on which we have f of a being strictly larger than or equal to f of x for all x in this subinterval c comma d, okay? So I restrict my view, basically, okay? I restrict my view. And it is, by the way, important for us to choose this interval to be an open interval, but I'll talk about that in a second. So we can find another point on this graph, which is going to not be a maximum, but it will be a relative maximum. And that's if we choose some a, which is right here, and we look at that point up there. We look at this point up here. Okay, if we choose C and D to be really close, and I just look at this snapshot of the function, which is between these two bars. Okay, if I just look at the snapshot of the function, which is between those two bars, then we do have a maximum at f of a. Okay. So this is a comma f of a. And we say that a comma f of a is a relative maximum. Sometimes we call this a local maximum. Okay. All right. Now, one thing that we should be one thing that a clever student might ask is, well, what if we chose C and D over here? What if we just choose C and D right here? And let me ask the class, is there a local or a relative maximum if we choose C and D to be this interval right here? What do we think? Let's have hands up for yes. Thinks yes, we have a maximum in this interval. Okay, decent number of people. Does anybody feel the opposite, that no? How about no? Let's have some hands for no. One brave student says no. Okay, in this case, the minority is going to be correct. So Catherine, bonus points to you. And let's explain why. Let me complete this sentence. There is no relative max in this interval. And here's why. Okay, here's why. The interval C comma D, which we chose, is going to be an open interval. Okay, it's going to be an open interval. So what that means is that this domain that we have does not include C and D, okay? It's just the stuff that's in between. Okay, so I can choose any point which is very close to C, right? I think we can all agree if there was a max, it would occur somewhere around here, right, on the left side of the interval. So I can choose any point which is very close to C, but not quite C. That's what it means for this to be open, right? So I could choose, say, maybe the point here, which we would call, why don't I use pink? We could choose this point here, which I'll call C plus 0.1. Okay, if we choose that point, then that's going to give us this point right here, right? Only the problem is I can get a little bit closer to C than that point, right? I could choose something like C plus 0.01, right? That's this point up there. And that would give me a point which is even higher than the previous maximum that I chose. So the point is, if I ask you guys for a number which is larger than C, I can always find a number which is even closer than C than that. And the height of the function at that point will be even higher. Okay? So the game here that we're playing is it's kind of like we imagine that there's like an open point here, and we can get as close as we want to it, but we can never reach it. And this is just to say that if any of these pink points were to be a relative maximum, well, I could take that point and take the x value and divide by or subtract some really small number and get a point which was even higher than that. Okay? So this is really just to say that it's not a given that we can find one of these intervals C comma D such that we have a relative maximum. It happened to be true between these points over here on the left because we had this max here in the middle. Okay, but if it's going up, like on this interval, again, we can't quite reach that maximum point on the edge because C comma D is an open interval with parentheses, okay? If we had brackets, then the right-hand side would be a maximum, but we don't. Okay? All right, any questions about relative maxes? Okay, if not, then we move on. So relative minimum is going to be defined in a similar way. If we have some function here, oh, that's not very good. Maybe it looks like this. Okay, so relative minimum is going to be if we can find a subinterval, an open subinterval, C comma D of the domain, on which we have that the value of that point is less than the value of all the other points in that subinterval. Okay, so this point here is going to be our, quote, absolute minimum. And this point here, we can take a subinterval around it. C comma D, on which that's the lowest point in the interval. So we call this a relative minimum. Okay, so when we're talking about relative minimums and relative maximums, we're really just talking about limiting our perspective. Okay, if we limit our perspective, is it the smallest or largest in that limited perspective? Okay. All right. It's kind of like, sometimes I talk about these in the framework of like student athletes. Sometimes people can vibe with that. You have people who are like you know, up at the tippy top, those are your people who are like winning the world championships, right? But then you have also people down here who are like, this is somebody who won like the state championship. And if we consider this subinterval to be like the competition in their state, then they were like the best in their state. But if we widen the scope of our search to include the nation or the entire world, then they're not quite the best anymore. So that's relative maxes and relative mins. So before, I'm going to move on to a different topic, but are there any lingering questions about maxes and mins? Okay, if not, then let's talk about even and odd functions. Okay, now even and odd functions, okay, when we talk about even and odd functions, we have a very, very, very different idea of what even and odd mean than when we talk about even and odd numbers, right? When we talk about even and odd numbers, we mean is it divisible by 2, right? If it's divisible by 2, then it's even. If it's not divisible by 2, then it's odd. Even and odd functions is kind of a totally different topic, okay? And here's how we define it. We say that f of x is even if f of negative x is equal to f of x. So in other words, it's symmetric about the y-axis. Okay, so that's what it means for it to be even. F of x is going to be odd if f of negative x is equal to negative f of x. And does anybody have an equivalent statement that we could put in these parentheses that's similar to the one above? What do we think? Is f of x being odd, is that going to represent some form of symmetry? Let's see if we can. We're seeing some people throw in symmetric about the x-axis. Let's try it. If we had a function which was odd, what are we saying? We're saying that if we have a value x here, and we have some point here, x comma f of x, we're saying that if we plug in the value negative x, so let's find negative x, that would be over here on the left side. What we're saying is that if we compute the value of the function at negative x, we're going to get negative of what we got when we computed it at x. So here should be the point x comma, or negative x comma f of negative x. And that should be true for all points on our function. So for example, if we were to draw this kind of like this, maybe it looks something like that. Then the other side, all of those points would be kind of flipped, but on the downside here. Okay, so looks like Om Kumar got it before I finished describing this. What I'm describing right now is symmetry about the origin. Okay, this is symmetry about the origin. Okay. Symmetry about the x-axis would be if we had something like this. That would be about x. Okay. But we don't have that. We have symmetry about the origin. Okay. All right, so that was kind of tricky. All right, so let's talk about how we actually kind of work with these definitions. And even and odd functions are a topic which again is really important when we come to calculus, because computing, well, how should I say this? Maybe I shouldn't talk too much about calculus, but I'll just leave it at the fact that even and odd functions are really important for calculus because they help us to compute things that we want to compute in calculus really easily. If we know that f of x is an even function or if f of x is an odd function, then it's super convenient to do calculus with those functions. So we like to learn those definitions here in pre-calculus so that when we get to calculus, it's a familiar concept. Okay, that's kind of the whole point of pre-calculus. Okay, so let's practice identifying whether a function is even, odd, or neither, because they can be neither. Okay, it's possible for neither of these two properties to hold. Okay, so let's try this one. We've got f of x equals x squared plus 2. So let's graph it. I always like to start with a graph when I know how to graph the functions. So x squared plus 2, how should I graph this? This is going to be a parabola, but what is this plus 2 going to do for us? Is that going to change our parabola in any way? We haven't totally talked about graph transformations yet. In fact, that's the subject of next lecture. We got some ideas coming in. 2 spaces to the right. Okay, well, it'll be good for us to go back tomorrow, or not tomorrow, but on Monday, we'll talk about these graph transformations. I think Aeon's got it. We're going to raise it by 2. Okay, remember, and we'll talk about this next time, if we had x plus 2 on the inside here, then this plus 2 would give us actually a shift to the left. X minus 2 squared, that would give us a shift to the right, 2 units. But when we have it outside, like we have it here, it's actually going to shift us up and down, okay? And here's why. What this equation says is basically f of x, in other words, the height of the function, should be the height of x squared, and then we should take that height and add 2. Okay, that's what it's saying. So we take a parabola and we just move it up by 2 units. So we go 1, 2. Okay, and by looking at the graph, I think we can see that we've already got symmetry about the y-axis. Okay, right? If we've got positive x here and negative x here, we're going to get 2 points and the height is going to be the same, right? Okay, so we can see graphically that we already expect this function to be even. But let's try to show this algebraically. Okay, here's how we'll show it algebraically. We just want to check whether this property holds. Is f of negative x equal to f of x? Well, we can figure that out quite easily by simply plugging in negative x. We want to know, is negative x squared plus 2 equal to x squared plus 2? What do we think? Who thinks yes? Let's have hands in the air for yes. Okay, a few hands. Any hands for no? Let's have hands for no. Okay, cool. Seems like everybody who is participating is in agreement. We've got negative x squared plus 2 is going to be equal to x squared plus 2, and that's true. Right? The reason being that negative x times negative x, the negatives cancel out and we just get x squared. Okay? So that's true. So this tells us that this is an even function. Okay, even function. Now let's try this one. F of x equals 2x cubed plus x squared. Now I don't really know what that one looks like. So I'm just going to have to rely on my algebraic principles, okay? Just the way that I can write this equation down. I'm going to try these definitions without looking at the graph. So let's just see if it's even first. We'll try the same process. Is 2 times negative x cubed plus x squared equal to 2 times x cubed plus x squared? Well, let's try. If we plug in negative x and we cube it, we get negative 2x cubed plus x squared equals 2x cubed plus x squared, question mark. The answer is no. So this function is not even. This function is not even. Okay. Now let's check if it's odd. If it's odd, what would be the case? We would have that f of negative x should be equal to negative f of x. Well, we've already computed f of negative x. That was negative 2x cubed plus x squared. And we just need to check is, why don't I use another color for this one? Well, we'll use another color for odd. Use red. We also want to check is negative 2x cubed plus x squared equal to, remember our definition for odd said negative f of x. Well, we know what f of x is. It's going to be 2x cubed plus x squared. We just want to check if this is true. We can check that fairly easily by distributing that negative sign. We'd get negative 2x cubed plus x squared is equal to negative 2x cubed minus x squared, question mark, and the answer again is no. Right? Because on the left-hand side, we have a plus x squared. On the right-hand side, we have a negative x squared. So those two things are not equal to each other. So we get that this function is not even and it's not odd. Therefore, it is neither. Nor even. Okay. So that's the game we play with even and odd functions. Are there any questions about even and odd functions? Okay, seems like no questions. If you think of anything, don't hesitate to interrupt. We're going to talk about piecewise functions. Now, a lot of students don't like piecewise functions. So my goal is for you guys to become familiar enough with them that they don't bother you anymore. Okay, so let's talk about what a piecewise function is. It's a function which has different rules depending on where you are, okay? And the description of where we are is always a description about the x values, okay? It's always a description about the x values. And the rule that's going to be changing depending on which x value we have is what should the height of the function be, okay? In this case, if x is less than 1, the rule we're going to use to figure out the height of the value of the function at that point will be we plug x into the function x squared. And if x is larger than or equal to 1, then we're going to use this other rule, 2x plus 1. Okay, so here's the algorithm for graphing piecewise functions. We just want to do the following. Let's make our coordinate plane. And the number one thing we're going to do, okay, is we're going to find where our function switches. Okay, our function switches rules at x equals positive 1. Okay, so that's what I'm going to immediately put on the graph. I'm going to put 1 on here right away. Okay. And what I'm going to now do is just to illustrate this, you don't have to draw this stuff, but just to illustrate this, I'm going to draw this kind of dividing line. Remember, an x value tells us how far left and right we are. So I draw this dividing line, and what this piecewise function says is that to the left, we're going to use the rule x squared, and to the right, we're going to use the rule 2x plus 1. Okay. Now, the main question that remains really is which rule should we use at x equals 1? And that's going to be this bottom rule, 2x plus 1, because in this case we have greater than or equal to, whereas we only use x squared as the rule if x is strictly less than 1. Okay, but when x is equal to 1, we're going to use the rule on the bottom. Okay, so let's try it. It should be, well, all we have to do is plug in the value x equals 1 into this. We just plug x equals 1 into this formula 2x plus 1. We'd get 2 times 1 plus 1 would give us 3. So we'll put a dot here at 3, and then from there on, it's just up at a slope of 2. Okay, the slope here is 2. And what does it look like to the left? Well, here's what we're going to do. We are going to plug x equals 1 into x squared, but we're going to put an open dot on that point. So if we plug x equals 1 into x squared, we would get 1, because just 1 squared is 1. So what I'm going to do is I'm going to put a circle here. Okay, and now to the left, I'm just going to draw the graph of x squared, which I know looks like a parabola. So I'm just going to take this parabola, which comes down and goes into there and then goes up like that. Okay, so it's kind of like what I could do, you know, is just draw both of these two functions. You know, I could draw both of these two functions in like completely, and then I could just find the dividing line and cut one off and say, okay, from here on out we're going to use this function, and from here on out we're going to use that function. Okay, oops, that's not my eraser. This is my eraser. Okay, so that's how I graph piecewise functions. All right. Okay, so we got 5 minutes left, and what I'm going to use my 5 minutes for is I'm going to rattle off the pictures of a whole bunch of really common functions which we sort of need to be aware of, okay? So these are things which I would recommend you guys to, like, I don't know, put on flashcards, sleep with the flashcards under your pillow so that you can absorb them into your brain at night. You need to memorize what these graphs look like, okay? Because you might have an exam problem or something like that, which will ask you, what does this graph look like? And you'll need to know how to produce it from memory, okay? You can always plug in points on a table, but that'll only get you so far. You need to know what is the shape of these functions, okay? All right. So I'm just going to go through these pretty quick. If we have f of x is equal to c, some constant, okay, we call this a constant function. And we just put a line right where the constant is. Okay, horizontal line. That's what a constant function looks like. Now f of x equals x, we know it's going to be a linear function, and in fact it's going to have slope 1, and it's going to have y-intercept 0, so it's just going to be the line which goes straight through the origin like this. Okay? All right, now x squared. That we all know is our friendly parabola. Okay, and the main difference between x squared and x cubed is, first of all, our rate of ascent on the right-hand side is going to be faster. Okay, because we're cubing these numbers. Generally, when we cube a number, we get something that's bigger than if we square it. Okay, at least if our number is bigger than 1. And the thing about cubing numbers is if we take a negative number and we cube it, we're going to get a negative number. So it comes in kind of like this and then turns around and goes down at the same rate. Okay, so that's x cubed. Next up, we've got absolute value of x. What does it look like? Well, it's going to be a V shape. Right? It's basically just the line that we drew earlier, except we reflect the instead of being symmetric about the origin, we make it symmetric about the y-axis. Okay, here's a tricky one. Square root of x. The way we draw square root of x is we put a point at 0, and it looks like just the top half of our parabola, which goes to the right. Okay? We choose this to be a function, and we write square root of x, and notably missing is the usual plus or minus. Okay, we're taking just the positive one. Okay, so we take just the positive, and this is what it looks like. Okay, if we took plus or minus, then we would get the whole parabola. But we don't want that because that wouldn't be a function. It wouldn't pass our vertical line test. Okay, so there's that. And cube root of x looks similar, except this one, we can do the cube root of negative numbers. 1 over x, and I'm running out of time here, looks kind of like this, because going to 0, when we start dividing by really small numbers, it gets really big. And on this side, it looks the same, but it's symmetric about the origin. Okay, what does 1 over x squared look like? It's going to look similar, except we're going to be positive on both sides. And yeah, okay, I'm out of time. I don't want to rush this, so we'll finish up drawing the rest of these next time, and then we'll do 1.5 on Monday. Okay, well, that's it for today. So if you don't have any questions, then have a great day. Thanks for watching. And if you do have questions, then stick around. Let me switch to my headphones and you can ask away. Yep, my pleasure. You have a good day too.
Hello, Professor.
Hi.
I want to ask you a question that's regard to previous class
Mhm.
lecture. I'm a little bit confused between when do I have to use the quadratic formula or factoring the
Okay.
quadratic.
Yeah, sure. Let me go back. I think I put some of these somewhere here. It wasn't there, I guess. Let's see, maybe it's in week 2. Um, what the heck? I know I put this somewhere. Okay, this is driving me crazy. I wrote out like a bunch of factoring problems at some point, and I was going to go over them with the class if I had extra time. Where on earth did those go? What? I'm losing my mind.
It's sunny out though, so. Oh.
Okay, well, I guess I'll just have to make some up for us. All right. So here's how I would answer your question. We want to, you can always use the quadratic formula if you want. Um, but if you have the skills to use factoring, a lot of the time it will be faster. Okay.
That's my main point, teacher, because I already have this course 2 years ago, and I'm pretty aware of using the quadratic formula. I just wanted to be sure I use it. I don't get involved in something like that.
Mm-hmm.
I don't prefer the sun.
Okay.
I don't
So let's try this one
care
here.
for the snow.
If we want to
Here,
factor this
after
or
having
find
to
the
walk to
zeros of
monastery
this, so we would
day in the
we would set
snow
this equal to
for
0.
6 years. Yeah.
Do you want to try using factoring or the quadratic formula?
If we use factoring, it will be x equal to either 2 or 3.
Okay, you're right, but let's factor
I
it first.
prefer
How would I
fall
factor
weather.
it before I get
Yeah.
x equals?
That's it.
Do you know how I would factor this?
Humid.
Like I should have 2 and 3 here, but what should go inside these parentheses? In these 2 blanks here?
Sorry, Professor, my laptop turned off. I switched to my phone.
Oh, okay. So what should we put in these 2 blanks? If we want to factor
Are you
this
moving by
expression.
yourself, or do you have someone to help you? Okay.
Are you there?
Okay.
I don't think I can hear your mic if you're talking.
Yeah.
Well, I heard you for a second there, but now you're gone again.
Oh God.
Can you try talking again? I think I heard you for a second there. Well, if you're speaking now, I can't hear you. I can just hear every now and then a click. Well, that's okay. What you can do is just hello, are you back?
Maybe what she meant is
Seems
she
like I
can't
still
assign
can't.
to this.
Oh, I'm hearing something. I'm hearing like some crackling. I think maybe what we should do for now is just communicate via the chat, okay? So, because I only have a couple minutes here. So what do we think should go in these two blanks here? Okay,